Hello people, this is a video tutorial for the second lab, or it's called a video solution for the second lab for mechanical, for the second lab for the mechanical 4259 computer aided engineering. This is the morning section. So the two problems to be done, and this is the first problem. It's kind of stated in an awkward way. There is some stuff here which you can ignore. Basically, what it says is that you have a frame structure like this. Use your own dimensions, use your own cross-sectional properties, and model this thing, and then push it to the force. And then if you want, the displacements that you get can be compared, displacement and rotation that you, at this point that you get can be compared with the analytical solution, which are given here from some stress analysis book. I don't expect you to do this, so make sure that you can actually model it, model this problem. And I'm going to, very few people actually did this. They mostly did the second problem, but I'm going to do this too, and I'll make sure that the cross section is not a circle, okay, so that we have another basically practice on non-circular cross sections, okay. The only restriction is that this angle is 45 degrees, and pretty much that's it. Now remember, there's no symmetry here. You cannot use symmetry, therefore you have to model the entire frame. Okay, so let's go ahead here, and I'm going to put it in a sketch. It's a very simple problem. So sketch. So let's draw something like that. By the way, my grid is not showing, so let me activate it. Okay, so something like this, and we're going to clean it up in a minute. Okay, so like that. Okay, first of all, let's make this thing. Horizontal. All right, and this angle. These angles, we're going to make it 45 degrees between this and that line. This problem is coming from the book. That's why it kind of has a strange write-up. Okay, good. That's pretty much all we have to do. Nothing else. So by the way, the dimensions that I've chosen, by the look of it, like this, for example, is roughly 7 inches. That'll give you an idea. Okay. So exit. These are dimensions of my choice. I'm going to create a point out here because I need it for orientation point. So I'm going to select the point, and I'll do it. Okay, what did I do here? Just a second. A point, coordinate 0, 0, 0, which is right here at the origin, right there. Okay. All right. So apply material on it. Let's make it out of steel, for example. Metal, steel on the part. Do not forget to join. You have to join it. Otherwise, you won't be able to measure it. Pretty much it. So we go to generative structure analysis. It's a very simple problem. It's not much you have to do. So mesh it first. Here's the measure, beam measure. You select this and use the standard number that I had from other two problems. 2 noded 0.02 inch element length. And we're going to put 1D property on it, another the shape of the cross section. So the support is right here. And the cross section, I'm going to make it rectangular. And for the size, I'm going to use, for example, let's make it 1 by 1 inch, just so that we can see it. Okay. Notice that immediately it put a kind of a 1 by 1 inch cross section on it, except that it won't let you close it until you select the orientation point. So for orientation point, I'm going to select this point, and notice that it kind of lines it up the way I want it. So this 1 by 1 inch cross section goes directly here, and then it continues, and then it goes down. Okay. Now you could have chosen other points. For example, this point could have been somewhere in the space. Then these things would have turned, and they may not be the orientation that you want. Okay. All right. What else do we know? These ends are clamped. So let's clamp this point. and that point. You can do it simultaneously if you want. And then you're applying a force here in the direction, that will be direction y. So there is a distributed force, which includes concentrated forces basically. And in the direction y, I'll put down 1,000 pounds. Okay, so let's see how it looks like. You can see it here, right there. See that? In the direction y. Okay. And that's pretty much it. You're going to run it and it's going to run, no problems. Nothing mysterious here. Just going to push this thing in. The shape is going to look like that. You can see that. See? If you look at the view from the front, it's easier to see what's going on. There we are. Okay. So the original shape becomes like that. If you want displacements, you're going to plot the displacement and change this thing to average ISO if you want full color variation here. So pretty much it. No big deal. Uh, I noticed that these are very small stresses. That's because this is a 1 inch by 1 inch cross section steel, and you're putting 1,000 pound on it. That's really nothing. Okay. That's pretty much it. This is first problem for lab number 2. I'll do the second problem now. For the yeah, this is problem 2. It says use symmetry to reduce the model as much as possible. Use the most appropriate elements. So you look at this, you have to realize that this must be done with beam elements. Do not do it with solid elements. Okay, and these ends are clamped. This middle point is pushed down by some amount, and you have to realize that the XZ is a plane of symmetry. So I need to model only half of this. Okay, and yeah, and we move on with the rest of the problem. So there's some dimensions given here. So let me see now. This is 3, and yeah, this is 3, and this is also 3. Okay, so let's go ahead and create our model. We have two choices. You can do it in a sketch, or you can do it in as a wireframe. That's entirely up to you. So I will do it as a sketch because it's easier. I'll model only half of it. So on that vertical plane, I will sketch something that looks like that L. So something like this perhaps. And we'll give it dimensions in a second. Okay, so let's see now. Dimensions. This is going to be 3, 3. Again, this is going to be 3. And this is going to be 6 inches. Yep. Okay, so there's my geometry. I exit because the cross section is a circle. I don't know what is the radius. 0.25 diameter is 0.25 inches. I don't need an orientation point, so this is fine. Yeah, let's apply material to it. Can't remember what was the steel. It says steel, right? Steel with default properties. Okay, good. So let's go ahead and apply material to this. Metal and steel on that part. We say OK, and do not forget to join. Now I just happen to be in generative shape design, so the join is here. If you were in part design and you did this thing in part design, you would have to switch to generative shape design to find join. Join, you cannot find it in part design. You click on it, you select that sketch, and it joins it. Okay, and now we're going to go to generative structure analysis. We're going to mesh this. Okay, I use the default element size, whatever I had in the last analysis. And then we're going to do the 1D property, make sure it's cylindrical, and make sure you click on the range, is correct radius. Now the radius is 0.125 because the diameter, I believe the diameter was 0.25, so this is going to be 0.125, okay? And of course the support is right here, and you can see that it put tiny little circle here, and same thing up there, etc. Good. So now this point is clamped. We're told that this point is clamped. All right. And this point obviously is in the plane of symmetry. So let me select this point. And since I don't want to mix up the issue of plane of symmetry with pushing down, so I say symmetry. This is a symmetry restraint. It lies in the XZ plane, so it does not translate in direction Y, direction 2, and rotations are exactly the opposite. In other words, because this is fixed, rotation is free. Because these are free, these translations are free, rotations are free. That's the way it works for symmetry. Okay, you may want to think about this thing, see whether it makes sense or not. Okay. It does make sense. Okay, so let me hide that symmetry restraint because I want to be able to pick this point easily. So do another one which says pushing down. We call this thing pushing down. Pushing down. Okay, so to push down, first we have to push it down by the amount 0. That sounds ridiculous, but that's the way it works in CATIA. And now we can go change it. So you go to enforce displacement, you select this, and you say negative 0.01. Okay, and this is pretty much it. I'm pretty sure it says 0.01, right? Yeah, 0.01. Oh, 0.001, sorry. Okay, no problem. So double click on this, put an extra 0 here. Okay, good. We're going to run it. Yeah, so a deflection like that. If you look at the view from the front, there we are. If you want actual numbers, you click on displacement. And if you want color, colorful contour plot, like that. Obviously, I pushed it down by 0.001. I don't expect anything to get here, anything else to get here. As far as the load that is needed to do this, because notice that these are coming from other, tests and things like that. At that point, these were the part marks that were given. Be aware of the fact that this is the way it was several years ago. Okay, uh, your scheme, your marking scheme may be different here, and you have to write down the magnitude of the force needed to create this displacement. You're gonna be asked to write down a number in this box. Okay? So what you do is you go and create your sensor. Right click, create a sensor, reaction sensor, and it says which reaction is it. You can select this top, the clamp, or you can select the restraint that you use to push down. Okay, and then update, and you get uh, almost minus 1 pound. Okay, now remember this is so low. That's because think about it, the diameter of this steel kind of hanger is I don't know, was 0.25, right? 0.25 is not a lot of diameter. So this is a very small amount. Now, the number that goes in this box is not this number, but it's the double of this number, okay? Because you're modeling only half of the structure now uh, in this particular problem. Now make sure that you say okay so that we have listening recording in your tree so that if you want to know where you got this number that you wrote down on your exam paper, we go to your tree, we better be able to find it there. Because otherwise we're saying that you just guessed it and that's not acceptable. Okay? Double of this goes in that box. Okay, that takes care of both problems. Good luck.